I am a singer, eternal voice. So let's continue uh, discussion and solving problems of thermodynamics. So let's go now with the problems. Okay, there are two problems to be solved right now. Okay, like that. So I want you to figure out what's really the mode of the problems presented. Okay, so that you can really identify what law of thermodynamics should be used, or whatever thermodynamics processes will be used also. Okay, for these problems. Okay, so in various thermodynamics problems, usually we use the first law and the second law of thermodynamics. Uh, for zero law of thermodynamics and the third law of thermodynamics, it's more on the theoretical aspects and concepts only. But here in first law and second law of thermodynamics are applied in different forms of thermodynamic problems. Could it be a basic or simple or easy thermodynamic problems, or it could be a more complex or complicated thermodynamic problems. So these two problems here are not really that complicated, okay? So we just have to use the uh, basic formulas presented in each thermodynamic law in the first law and second law of thermodynamics, and then we can solve what is being required, and in combination with the analysis with the behavior of gases, the ideal gas law equation like this, and we can correlate those formulas and equations and the rest of the formulas of science. Okay, that's why we have uh, prerequisites science subjects taking up our major science subjects, right? Because it's really helpful, or it's really important. Okay, now we try to solve this one. So I will read first the problem. Okay, what is the change in internal energy of system which does 4.50 times 10 5 joules of work, while 3.0 times 10 to the 6 of heat transfers of course into the system, and 8.0 times 10 to the 6 joules of heat transfer of course to the environment. So before going further, so we need to explain a little bit with the heat transfer from a system to the surrounding. So, for example, if this is a system and this is a surrounding, the system is the source, okay, where the heat is originated, and our surrounding is the environment where the heat is being transferred, or where the heat is being circulated, something like that. Okay, so if the heat is being released to the environment, meaning to say the heat is removed from the system, so that is negative heat. Okay, and then if the heat is added to the system, okay, and then it is being absorbed to the system, okay, and it is being received to the system like that, so that is a positive heat. So here in thermodynamics, we focus on the system mainly as our reference point, not to the surroundings. Okay, sometimes like that. Okay, because in chemistry also, we focus more on the surrounding, to the environment. What could be the effect in the environment or in the surrounding after the chemical reactions took place? Okay, something like that. So that's it, something like that. Or the heat absorbed, the heat released, our reference is the system or the source, something like that. Okay, now we go now to the problem. Okay, so in number one, we are asked for the change in internal energy. So it's very obvious. So you can think that there are two formulas of internal energy, right? So we have the second law and the first law. Okay, so in the first law, we have change in internal energy is equals to Q minus W. So this is the first. Okay. This is in the first law of thermodynamics. Change in internal energy is equals to the heat energy transferred minus the work done by the system. Something like that. Okay. We have also another formula which is taken from the entropy formula, right? So we have delta gives free energy is equals to delta U minus that enthalpy. Or we can say this delta G is equals to delta U minus heat alone. Okay, so like this. So from the second law of thermodynamics, we have delta change and gives free energy, which is the spontaneity of the process. Okay, like that. And then we have the change in internal energy minus the heat transferred, or the heat energy transferred. So if there's a changes of heat from the system and from the source, so we need to use this delta H. But if there's no changes in heat from the source and from the system, so just H. Okay, it's just like that. Same also with change in internal energy. If there's no change in internal energy from the from the first system and the second system, like that, so it's only internal energy, something like that. Okay, so the delta here represents the changes only. Okay, something like that. If there's no change, then just have it as internal energy, or just have it as a heat or enthalpy, and then or gives free energy, something like that, if there's no changes or there's no gradients. Okay, something like that. Okay, the heat and the enthalpy will just be the same in concept, heat energy transferred, but the enthalpy is more on the total heat content. Okay, and the heat is just a simply heat, whether it is not a total or not, something like that. So this is my second law of thermodynamics. So in the problem number 1, we have to find change in internal energy. So that is delta change in internal energy. So this one. So this is the required in problem number 1. So we can use this equation, the first law of thermodynamics. Okay. In the problem class, it's talking about the heat, okay, transfer occurs into the system. What's this heat? The heat transfers occurs into the system. So meaning to say, this is added to the system, because heat transfers occurs to the system. So this is a passive heat. Okay, this is a passive heat, which is equal to, let's say, Q1, represent as Q1. 8, okay, 3 0 times 10 to the 6 joules. And then take note also that we have other heat here, which states that heat transfers occurs, and heat transfers occurs to the environment. See, heat transfers occurs to the environment. The other one, heat transfers occurs to the system, and heat transfers occurs to the environment. We need to say this is the heat occurs to the surrounding. So this kind of heat was given off from the system. So this is a negative heat. Okay, something like that. Okay. So Q2 is equals to a negative 0 times 10 to the 6 joules. Okay, like this. this is a negative heat, which is 8 times 10 to the 6 joules, because it is the heat transferred, of course, to the environment or to the surroundings. It was the heat given off from the system. Okay, like that. So we can solve this as total heat content Q is equals to Q1 plus Q2. So we can have total heat, okay, is equals to Q1 plus Q2. Heat transferred, of course, to the system plus heat transfers, of course, to the environment or to the surroundings. So Q is equals to Q1 plus Q2. Then put the values of heat now. Okay. Or we can also write as the total enthalpy here is equals to Q1 plus Q2, something like that. Or you can use also this if you want. Total heat content transfer delta H is equals to Q1 plus Q2. Because basically, enthalpy is just a heat content, total heat transfer content, just the same with this Q here, something like that. Okay, so we'll just use this equation so that it will be more easy. Okay, so Q1 is like this. So 3 times 10 to the 6 minus 8 times 0 times 10 to the 6. Okay, so we have 5 times 10 to the 6. So if we add the 2, so Q1 is equals to 3 times 10 to the 6 joules. Okay. And the other one is 8 times 10 to the 6 joules. Okay, then he transferred to the environment. Okay, like that. So we have the delta U is equals to Q minus W. So use the equation number 1. So delta U, we have negative 5 times 10 to the 6 joules. Okay, and then we have the work done. Work does a 4.50 times 10 to the 6. Okay, so minus, this is which does energy, this is negative work, so minus 4.50 times 10 to the 6 is equals to, okay, 5 so 5 minus 4.50. This is 5, right? Sorry. So when 0, 0, 0, 0, 450, so 1, 2, 3, 4, 5. Okay. Minus 0, 0, 0, 0, 0, 5. 1, 2, 3, 4, 5, 6 equals 10. So 4, okay, 4 times 10 to the negative 5 joules. So this is our answer. Okay, since delta U is equals to Q minus W, right? And then our heat is already computed here, okay, and then transfer that here, okay. So we obtain change internal energy, which is equal to 4 times 10 to the negative 5 joules. So this is our work, 4.50 times 10 to the 5 joules, okay, which does by the system, okay. So that is negative, that's okay, 4.50. So work that's by the system is 4.50 times 10 to the joules, 10 to the 5 joules, sorry, 4.50 times 10 to the 5 joules work. Substitute for this equation, okay, like this. Delta U is equals to Q minus W, and we have the Q already computed here, then minus the work, which is like this, then this answer will be like this. So this is only a computation, directly substitution, okay, like this. Okay, so the answer will be 4 times 10 to the negative 5 joules. Okay, so because we obtain a negative heat, okay, because we have an 8 times 10 to the 6 joules of heat transfer, of course, to the environment. So that is negative shock that is coming from the system. Okay, because we are referring for the systemic shock. Okay, then our heat transfer, of course, into the system, of course, is a positive heat. So 3 times 10 to the 6 minus 8 times 10 to the 6 minus the work, which is 4.50 times 10 to the 5 joules. Muna na siya answer. So yun na kayo siya. Very easy. Okay, directly substitution. Okay.